Welcome back. Today is this is COL 774 machine learning, and today is April 28th, 2020, Tuesday. Sorry, Wednesday it is. Okay, last class we started looking at learning theory, right? And we were really looking at learning theory in the context of generalizability, right? And the idea was that, let's say, given a classifier, right, or a regressor, doesn't really matter, right? But since we are dealing with classification problems, uh, right, in the context of learning theory, so let's take a classifier, right? And this was our standard example of monkeys and chimps, right? These are chimps and these are monkeys, right? And these are our attributes: weight and height, right? We were really interested in, right now, suppose we learn a hypothesis, right, which is h theta x, right, using some training data. Then we were really interested in the generalization capability of this learned hypothesis on the training data, right? So given a new example x, right, suppose the prediction is y hat, then how close is y hat to, let's say, y, which is sort of the original prediction or original label, or true label rather, right? So we are really interested in, right, that if your hypothesis does well on the training data, which is, what we optimize the error over the training data, then, what can you say about its performance on unseen examples, right? And in this context, right, we started dealing with learning theory, and we made a certain set of sort of assumptions, right? So in fact we went, right, we talked about certain assumptions in the form of having test and train having same distribution. We also talked about inductive bias, in terms of, assuming that simpler hypothesis generalize well, will formalize that notion. And we also intuitively talked about, effect of number of examples, right? And we'll sort of bring all these things together in today's class, right, or maybe in the next class, right? And then we talked about the setting that we were in. So let me just write here. So the first was that all your training examples, right, come from some underlying distribution, right? And also your test example xy also comes from the same underlying distribution, right? So this was sort of one starting point. And then we said, let me use a different pen. Second, we said that we are dealing with classification tasks, and that too binary sort of classification task. So our yi will be between 0, it will be the set 0 and 1. I think the results, right, many of the results could be generalized to more uh, discrete settings, and maybe I think continuous spaces, but let's, for the purpose of this class, let's focus on just the classification, binary classification setting. The third thing that we said, that initially we'll assume that we are dealing with a finite hypothesis class, right? And sort of the fourth thing, right, or which was actually sort of maybe in between, somewhere, I mentioned that, uh, that right, let me just write it as to 1 and 1a maybe, that given m examples, right? Right, so this is right, this is another important point, that we'll assume that we are given a certain data set with a fixed number of examples, and then we'll show dependence on m, right? So the test and the train have the same sort of distribution. Then when we are given a fixed number of examples, right? So m examples drawn from that distribution, which are our training examples, and we learn the hypothesis on that. And we are dealing with binary classification tasks, and initially we will deal with finite hypothesis classes, but we'll sort of generalize it to continuous or sorry, to infinite hypothesis classes also, right? Okay. And one more sort of assumption that we made, or one more, uh, you know, uh, notation that we will use is, we defined epsilon hat h, right? And this is, given some, right, small h belonging to the hypothesis class. Epsilon hat h is the training error of this hypothesis on the training examples. So error on the training examples of this hypothesis, 1 by m, right? And we also defined epsilon h, which is sort of our generalization error, and this was our training error, and this was defined to be expected value of xy coming from this underlying distribution, right, which is same as the distribution from which training examples are drawn, of indicator of hx not equal to y, right? So this is, the expected performance on the unseen examples, right? And as we will see, we will try to bound, right, difference between these two quantities, right, for all h, right? Because epsilon hat h is something that we really know on the training data, but epsilon h is the error, or the quantity that we are really interested in, and we'll try to sort of create a bound on this quantity, right, which will tell us, how good of a predictor is epsilon hat h of epsilon h, which is the generalization error. And what we will do in this context is we will say that, this, there will be probability that will be associated with this quantity uh, being, let's say, more than some number gamma will be less than equal to some number delta, right? So what we will do, as we will see very soon, is that we will say that, we will not make a deterministic statement. We will say that the probability that, the difference, the absolute sort of difference between our training error and generalization error is more than gamma, right? So this is sort of your error bound, if you will, right? Is really less than equal to delta, right? And this is in some sense your confidence, right? And these are the kind of bounds, or these are the kind of results that will derive, right? And that's why, right, because of the form that we see here, these are called back learning bounds, where back stands for probably, approximately, correct, right? And this name is interesting because there are two sort of uncertainties here, probably and approximately, and note that, they have very specific meanings, right? This part is, probable or probably, right? This quantifies probably, and this quantifies approximately, right? So with a certain confidence, right, which is, 1 minus delta, right, or with probability at most delta, right? We'll see that we can write it both ways, right? We can write it, the difference is more than gamma is less than equal to delta, or we will say that difference is, uh, sorry, let me repeat, we can say it both ways. We can say that the difference is more than gamma, that probability is less than equal to delta, or we can also say that the difference is less than equal to gamma with probability at least 1 minus delta, right? So we'll look at it both ways, but I think what is important is that the probability part comes from this delta, which is the confidence in our statement, and the approximately part comes from how much is really the difference or the error between epsilon hat h and epsilon h, right? So that difference essentially is something that we want to bound with a certain probability. Okay, so these are the kind of bounds that we will derive, and we will derive them in terms of these four quantities that I will write here, right? Those will be the quantities of interest, and they will also relate to what, right, we have sort of seen earlier. So first one is m, number of examples, right? We will see that these bound actually depend on how many examples are there in the training data, right? And that's where a training data of a particular size, having that assumption becomes important. It will also depend on size of the hypothesis space. Okay, then the third one, of course, it will depend on how much is the error bound that we are able to tolerate, right? So this is our error bound. And the fourth one, right, that will derive these bounds in terms of is delta, that is our confidence parameter. And LC will often write results in terms of uh, probability being less than equal to delta of making an error, or probability being at least 1 minus delta of being within this error bound, right? So we'll look at both sides of results. So before we proceed, there is one more right sort of diagram that I want to draw, and that will also sort of add to the intuition, right? So suppose this is your space of set of all set of all possible examples, right? Or set of all possible instances. Let me write it that, right? So this is essentially representing all your xy pairs in your universe, right? And what happens is that training set essentially is this set which is a subset of this all possible examples in the universe. And note that this example of universe, uh, universe of instances could potentially be infinite, right? Typically it will be, it could be potentially infinite, right? And this is our training set, and what we do is that given this training set, right, we learn a hypothesis, right, which is h theta, often it can be parameterized by these theta parameters, right, which belongs to our the class of hypothesis, right? And we'll deal with both finite and infinite hypothesis, right? And then the error on these set of examples which are sort of in this box is given by epsilon hat h of indicator of yi not equal to hxi, and then sum over all examples, right? And now the question is, right, suppose right after, right, and of course this h theta is learned by minimizing sort of training error, right, on these examples that are seen, right? So we sort of find that h which minimizes this, but the results that we will derive in fact will be sort of for all hypotheses, right? We'll see that will our results will sort of say that if you take any hypothesis, right, in the space, right? So if you take any h belonging to h, then we'll be able to sort of bound the difference between epsilon hat h and generalization error, which is uh, um, right. So we'll be able to bound this difference between the training error and generalization error, which is epsilon h, right, which is defined to be, uh, let me sort of give you the intuition that suppose now, right, so you are given this training instances, and suppose you are also given this hypothesis, right, this h belonging to h, right, and then you get a certain training error. um, uh, right? And typically we'll pick the one which is best on the training set. But let's say you pick some hypothesis and you compute the training error. Now the question is, if a new test example comes in, right, which is somewhere in this space. In fact, right, this is any example, right, in this space, right, and it's sort of a random sample from this space, right, and this space itself may have a distribution over examples, right, but in some sense we are drawing from this that distribution, right. So then the question is, right, what is sort of my expectation that my hypothesis, right, which I picked now, which is H, will do well on this particularly randomly drawn example, right? And this is nothing but the expected value that xy is drawn from this underlying distribution, right, which is essentially this entire space, right? And the expected value under this distribution of indicator of y not equal to hx. Right, and what we are really interested in now is that how good of a predictor is epsilon hat h of epsilon h, right, and we want to really bound this quantity, right, with high enough probability, right, and right, that's where I said that we would derive these bounds for all h, right, belonging to the hypothesis space, and then we will say some more interesting results for the the hypothesis which does well on the training data, right. So that's sort of the schematic of things. So what we'll do is we will take a slight detour and look at this coin toss example, right, which is a simple example, uh, and we will about tossing a biased coin, and we'll derive some results which will be useful for the kind of results that we want to prove in our context, for relating epsilon h and epsilon hat h, and these will essentially be sort of derive a bound or inequality called Hoffing inequality or Chernoff bound, right. We may not sort of derive the entire bound, will rather state the result, but we'll describe the setting and we'll state the result in the case of coin toss example, right, and then we'll relate it to our the problem in our context. Okay, so what we right, so assume that you are given a biased coin, right, and you toss it a certain number of times, let's say m times, right, and let z denote the random variable, right, which is the outcome of the biased coin, which is belongs to 0 to 1, or they said 0 and 1, and z, let's say, is coming from this distribution which is Bernoulli of phi, right. So this z distribution is Bernoulli of phi, uh, right, and given a number of such coin tosses, right, let's say m tosses, right, what we are interested in is really estimating our parameter, which is phi, right, which is the parameter of the Bernoulli distribution, right. So now let's see what happens, right. Suppose, right, I right, and what we'll do is we will call this entire sort of the sequence, right, or the process of tossing it m times, right, collecting these zi's, right, and estimating phi as one experiment, right. So this is our experiment number one, right, that we take the biased coin, right, we don't know what is its sort of underlying probability of turning, let's say, head, which is essentially the parameter phi, right. So we toss it m times, right, m could be some number, let's assume, right, for just for to ground things, let's say m is 100, right, but this is sort of a general result that will derive, but to make things rounded, let's say m is 100, right. So in the experiment one, let's say we see 57 heads, right, and head is, let's say, 1, and 43 tails, right, and given this, right, so our estimate, right, in this experiment 1 of v hat of v, let's denote it by v hat, is nothing but how many times did we see the coin to be head, right? Which is essentially zi, right? I equal to 1 to m, 1 by m, right? And note, remember that head denotes 1 and tail denotes 0, right? So this is right. So head, if it's a head, then it means that the coin, then zi is 1, and if it's a tail, the zi is 0, right? So this is our estimate, and in this experiment 1, this estimate will be 57. If 57 ones were observed out of total 100 examples, right? So this was our experiment 1, right? And now clearly, right, our estimate for fee here is 0.57, but clearly, this may not be exactly what fee is, right? Maybe fee is 0.56, maybe fee is zero point 0.6, maybe fee is 0.43, and we just got lucky, and we got more number of heads, right? But what we'll see is that, in fact, fee hat is what we refer to as unbiased estimator of fee, right? And we will sort of define this more formally. Maybe some of you have seen this in one of the stat classes, right? But let's keep going, right? Suppose, right, let me draw a line here, right? So this is experiment 1. Now let's say we do an experiment 2, right? And we do the same process again, right? We say, okay, now let me toss this coin again and 100 times, right? So I'm repeating this experiment, and remember, the experiment is 100 tosses of this and this biased coin, right? Each toss is IID, right? Which comes from this Bernoulli distribution. And in this experiment 2, let's say we get maybe 49 heads and 51 tails. Okay, so then what is, you may ask, what is my estimate of p hat, right, in this experiment 2? And then you will say again, it is 1 by m, I equal to 1 to m summation zi, right, which in this case will be 49 over 100, right, which is 0.49, and this is 0.57, right? And right, if you will, right, just to sort of if you wanted, right, we can also denote this by the superscript phi hat 1, phi hat 2, and so on, right? So this is just saying experiment number, right? And make sure you differentiate it from the zi's, right? So zi's are the i's denoting the index, example index within that experiment, right? And not to clutter the notation too much, I'm not you know uh, adding another subscript over z, right, which denotes the experiment number, right? But the difference between the subscript of superscript of phi hat, which is the experiment number, and the superscript of z is actually the example number within that experiment. Okay, so we can keep going, right? So we can say that, okay, maybe we do an experiment number which is t, right? And we get phi hat of t, right? In the tth experiment, we, let's say, we obtain this time we got lucky, and we say 59, we obtain 59 heads and 49 tails. And what will be our estimate? Our estimate will again be I equal to 1 to m zi, right, which will in this case be 59 over 100, which is 0.59, right? And then you can keep going, right? So you can do it potentially infinite number of times, right? So now the question is, right, given this sort of setting, right, what is our guess about, or what is a way of what is a good estimate, or how do we really estimate fee, right? Or in other words, right, this is sort of a hypothetical experiment, right, where we have done this experiment t or a large number of times. But the key thing to note here is that what will happen in reality is that we will do this experiment once, and we'll get some phi hat, right, corresponding to one of these experiments, and we'll say that this is our estimate of phi, right? And note that this phi hat, for any given experiment, is also a random variable, right? Because if we look at this expression, right here, right, this is simply a sum of these zi's, right, which is a set of random variables, and right, 1 by m is just dividing by number of examples, right? So this sum average of these random variables is also random variable, right? Because zi are random variables, and phi hat t is the random variable that we're interested in, and then we'll look at some properties of this phi hat t. And we will see that this phi hat t is in fact very closely related with our training error, and in fact the phi parameter is very closely associated with the generalization error that we talked about in previous slides. So let us look at some properties of this quantity, right? Phi hat, right? And I'm removing the iteration number, sorry, the experiment number, because just a random variable, right? And we can talk about this estimator in general, right? That right, which is simply this sum of these zi's, right? We toss this coin m times, we observe the corresponding zi's, right? Zi being 1 if it is a head, and 0 if it is a tail, and then we sum these random variables and then take 1 by m of this, right? Now this implies that because it's a sum p hat is a random variable itself, because it's average over an average of random variables, therefore we can talk about expectation of this p hat under the distribution, right, of these zi's, right, given that these zi's are coming from Bernoulli phi, right? So this e phi will simply be 1 by expected value of 1 by m I equal to 1 to m of zi, right? And from linearity of expectations, right, this quantity is nothing but 1 by m comes out, and sum over 1 by m I equal to 1 to m zi, and once again, right, following linearity of expectations, right, we get we can take the expectation inside, so this becomes 1 by m I equal to 1 to m expected value of zi, right? And note that now, that what is zi, right? Each of these zi, recall that each of these zi was nothing but Bernoulli of I, right? So each of these zi was coming from this underlying Bernoulli phi distribution, and the expected value of a Bernoulli random variable is simply the probability of head, or probability of coming out to be 1. It's a very simple result that you can derive in just one line, right? So therefore it becomes 1 by m into expected value of zi, right, which is simply because it's probability of 1 p into 1, which is p, plus probability of 0 1 minus p into 0, so right, so it becomes p, right? So or phi, right, right, our p is phi, so this is just phi, so this is m into phi, and therefore phi, right? So what essentially we have shown here is that the expected value of our this estimator phi hat is nothing but p, right? And this is an important result, and the expected value of our estimator, which itself is a random variable, is equal to the actual quantity, right? And such estimators are called unbiased in statistics, and they are very important because in some sense, on an average, they are unbiased, right? On an average, in expectation, right, they do the right thing, right? But right, and let me just call it sort of a, right, and but this may not be enough, right, to really quantify, right, what is a good estimator, right? Because we also want to understand its dependence on m, and why is that? Because in this expression that we have done here, or in this calculation, right, there is no dependence on m, right? It's sort of always unbiased estimator of phi, but the challenge is, right, or the insight is that intuitively we understand that as we have large number of examples, right, we get a better and better estimator, right? So right, we right, or in other words, right, in fact, let me do it other way around, that I have computed the expected value, let's also look at the variance of this estimate, right? Let's not worry about what directly about number of examples. Let's just look at the expectation of this, right? We want to understand the properties of this estimated phi hat, and the expected value is phi, which is great, but let's also look at the variance of this phi hat. Okay, so then we get variance, which is nothing but variance of 1 by m. Let me just clean this slide a little bit. Okay, so variance of 1 by m summation I equal to 1 to m of zi, okay, and variance of this quantity. And we know that variance of k times a random variable is k square times variance of that random variable, so it becomes 1 by m square variance of I equal to 1 to m zi. Okay, now because these zi's are IID, right, and the following result holds for only for IID random variables, right? Variance of or I guess we don't need identically distributed, but variance of sum of independent variables is sum of the variance of those independent variables. Therefore this becomes 1 by m square I equal to 1 to m and variance of zi, right, each of the zi. Okay, now as an aside, right, what is the variance of each of these zi? And again, a result that I will not derive it here, but please go back and show that the variance of this zi, which is a Bernoulli random variable, is nothing but p into 1 minus p, right? And right, just derive it as a homework, right? This is a small little exercise, right? um, and remember that the variance so please go back and derive this, right? I will not derive it here, right? So this is just go back and derive that variance of a Bernoulli random variable is simply phi into 1 minus phi, where phi is the parameter of the Bernoulli variable. Okay, therefore we get what we get here is 1 by m square, and all of them are identically distributed, so we get 1 by m square into m into variance of zi, which is phi into 1 minus phi, right? And we can cancel this, so we get variance of this phi hat is phi into 1 minus phi, which was sort of the variance of the original zi's, but now we have also 1 by m, right? And this is what I really wanted to refer to in our sort of earlier discussion, right? So this expression is phi into 1 minus phi divided by m, right? Now note that although the expected value does not depend on m, but variance does depend on m, and in fact it goes down, right? Inversely, it's sort of inversely proportional to number of examples, and that is the key, right? That although our estimator was unbiased, right, but its quality also depends on number of examples, because as we have more examples, there is we observe less variance in the estimate of p hat, and right, that is a good thing, right? And that's why this both right, being unbiased is important, but having low variance is important, which means we have to have a sufficient number of examples for phi hat to be quote unquote a good estimator for phi. Okay, and yeah. So given sort of the intuition on the previous slide, right, about the 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 expected value of phi hat being phi, and variance of phi hat being uh, simply phi into 1 minus phi over m, right? And the fact that variance gets better or less and less as with increasing number of examples, right? But what we are really interested in is now the relationship between phi hat and phi, right, for a given number of examples, right? So if we estimate our phi hat as phi hat is summation over zi I equal to 1 to m 1 by m, right, which is our phi hat, and each of these zi is now coming from this Bernoulli distribution, right, phi. And on the previous slide we showed that expected value of phi is pi or phi, and variance of this estimator phi hat is phi into 1 minus phi over m, right? But this is fine, right? But what we are really interested in is bounding the difference between phi hat and phi, right, given a certain number of examples, right, over which this experiment is carried out. And that is where the result about this hopping or bound, hopping inequality or Chernoff bound comes in. That, and I'll state this without really proving this result. The result says that the probability of this phi hat minus phi, the absolute value of this being more than some quantity uh, gamma, right? This entire probability is less than equal to delta, right? So this is the result that we will use, and this is called the Hoffing inequality or Chernoff bound, right? So this, once again, what it is saying is that, right, and you can see the probably and the approximately part coming in. Of course, this is in the context of this phi hat and phi, but in the next slide we will actually connect it with our problem, which is epsilon hat h and epsilon h. But let's just read it again. It is saying that the probability that our estimator phi hat is not, or rather is far away from phi, where the definition of far is more than gamma, this probability is less than equal to delta, where in fact I should have stated this delta is 2 uh, e to the power minus 2 gamma square m, right? So let me just write it again. So the inequality is saying that the Hoffing inequality or Chernoff bound says that probability that phi hat minus phi is greater than gamma, right? This probability is less than equal to 2 e minus 2 gamma square m, right? So this is our result, right? And note sort of the dependence on m, that as m increases, right, this sort of delta, right, decreases exponentially, right? So as we have more and more number of examples, right, we are able to bound this probability very well, right? And that makes intuitive sense, right? With larger number of examples we have a sort of a tighter bound, right? And we will sort of connect this now with our setting in the next slide. Okay, so let us revisit our this coin toss experiment, right? So we have collected these zi's, right, I equal to 1 to m, and then we had an estimator, right, which is phi hat, which is nothing but average over these zi's, right, average of the zi's over all these m examples, right? And this phi hat was essentially an estimator of phi, which is our sort of underlying Bernoulli parameter, right, which is nothing but really the underlying probability of the coin turning out to be head, right, or one in our case, right? So now let us see that there is a very interesting parallel with the problem that we are trying to solve, which is remember, we have this epsilon head h, right, which was right, and right, in this slide we'll assume that we are given a hypothesis h, right? So we are given some hypothesis, right? This h belongs to some h belonging to h. Okay, so this epsilon head h was nothing but indicator of yi, right, not equal to hxi, right? This was our sort of training error, right, on this particular example I, and I equal to 1 to m and 1 by m, right? And I'm using the same m for a reason, to draw a parallel between these quantities, right? And in this case the examples were xi, yi, I equal to 1 to m. Okay, and then we were really interested in was epsilon h, which is sort of the expected value of xy, it coming from this underlying distribution, right? This is also the same distribution from which right, each of these training samples were drawn, right? And expected value of the performance of this hypothesis on an unseen example, which is indicator of y not equal to z. Okay, and what is interesting is that, right, let us also specify the distributions on the left side, right, where I is Bernoulli of phi, right, and and each of these come from this distribution, and note that this phi is right for a Bernoulli random variable. We know that the parameter is nothing but expected value of a variable z, right, where z is drawn from this Bernoulli distribution. Right? This phi is nothing but the expected value of this Bernoulli random variable. Right? So we can write phi, the parameter of the Bernoulli random variable, as also the expected value of the random variable itself. Uh, uh, Okay, right, so there is an interesting parallel that you can see here, right, that these ZIs, right, if you look at carefully, right, in fact, what we can do here is that, right, as an aside, right, or as an additional sort of detail, uh, right, we can define these variables here for every example, right, which is indicator of yi not equal to hxi. Right, so for every example, right, given this hypothesis h, right, we can define this indicator of yi not equal to hxi, and now you can see a very clear parallel between the left hand side, right. So this is LHS, and this is our RHS, right. There is a very clear parallel that our ZIs are nothing but essentially corresponding to these indicator variables, right, which is given a hypothesis, right, whether for that particular example the hypothesis makes the correct prediction or not, right. And what is sort of the random draw here? The random draw here is the example, right, that you draw from the distribution, right, this xi yi coming from the distribution, right. So you sort of draw this example, right, and check whether your hypothesis does correctly or not on that, and that is your indicator of this quantity yi not equal to hxi. But I can almost interpret this as my zi here, right, on this side, right, because this is 0 and 1, and it's sort of a random draw from this set, right, of examples, uh, right. And then you may ask, what is essentially the underlying distribution of this random variable on the right hand side? And this is exactly epsilon h, right, because what it is saying, this epsilon h is exactly the probability that if I were to draw a random example which is xy, right, from the underlying data set, right, from given the distribution, then uh, this epsilon h is exactly the probability, right, of this hypothesis doing correctly on this randomly drawn example, right. So note that this uh, uh, right, I think what might be illustrative here is that the error, right, this particular error, this indicator yi hxi, right, this is the expected value of this, right. So let me just write something here which will make it clear, maybe, right. So let me know if you agree. The expected value of this indicator yi not equal to hxi, uh, of this, where xi yi is also drawn from this distribution, is also equal to epsilon h, right. So in some sense what we are saying is that because the training examples were also drawn from the same distribution, right, the expected value of each of these indicator variables, which is essentially our zi, is epsilon h, and which is like the Bernoulli parameter of if you were to treat this as sort of a Bernoulli experiment, right, the parameter of that epsilon, that Bernoulli experiment, is this generalization error, which is epsilon h, right. This is our generalization error, right? And each of these training examples, the error on those are like zi's, right? And therefore we can estimate our epsilon h, which is our generalization error, which is like the phi parameter on the left side, by this training error, right? Average training error epsilon hat h, which is like, you know, average of these zi random variables, right? Therefore, right, right, what we'll see is that we can analogously, right, because of the way of this correspondence, right, we can apply Chernoff bound, right, or Hoffing inequality that we saw on the previous slide for over, you know, right, over epsilon hat h and epsilon h, right, treating epsilon hat h as an estimator of epsilon h, right, and using this correspondence we can apply the Chernoff bound or Hoffing inequality, and we will see that application on the next slide. So given the correspondence on the previous slide, right, what essentially remains is just to state the result that we have for, you know, relationship between phi hat and phi, right, where phi hat is estimator of this Bernoulli parameter phi using, you know, uh, m trials, right. So this is probability of this phi hat minus phi, this estimator phi. Phi is greater than gamma is less than equal to delta, right, where delta was 2e to the minus 2 gamma square m, right. And then, you know, by having, by the way of correspondence, right, between phi hat and epsilon hat h, right, that we talked about on the previous slide, right, the probability of this being greater than more than gamma is less than equal to 2e minus 2 gamma square m, right. And this is essentially our version, right, or Hoffing inequality or Chernoff bound applied to our setting, right. And here note that, you know, this is for a given h belonging to h, right. So someone gives me an h, and for that particular h I can state this result, right. Uh, but what we are really interested in is sort of stating this result, that, you know, um, for all hypotheses together, right. So this is sort of stating them it for right, independently for each hypothesis, right. So if I give you an h, right, the probability that uh, this difference is more than gamma is less than equal to um, this right hand side, which is 2e minus 2e raised to the power minus 2 gamma square m. But we would like to be able to state this simultaneously for all hypotheses uh, in our hypothesis space, and that's where this union bound comes in, right. And what is this union bound? This union bound is a very simple result, which is, you know, again, an aside, and then we'll relate it to our case. It says that suppose, you know, a1 up to a k are some events over a probability space. Okay, so given some probability space, you know, a1 to ak are some events which are not necessarily disjoint, right. Then the union bound says that the probability of a1 union a2 up to ak is always guaranteed to be less than equal to, if I take the probability of each of these als, right, and then sum over L equal to 1 to n, right. So the probability of a union of events is less than equal to the sum of the probability of the individual events, right. So this is a standard result from the probability theory called union bound, right, and we will apply this to our case in the next slide. So we will assume that, you know, the size of the hypothesis space is a, right, and then we have the result that for any given h belonging to h, right. So this is for a given h belonging to h we have, right, and this is any given, right. We can take sort of any hypothesis, right, in the space, and then we have that the difference between the training error and the generalization error of this hypothesis being more than gamma, this probability is less than equal to 2e minus 2 gamma square, right? And now we want to state this for all hypotheses taken together, right? So we'll apply uh, the union bound, and we'll say that, what is right if we right. And now let us define an event al as the event that epsilon h uh, L, right? So this is for any given hypothesis, right? So let's say, there is some hypothesis HL belonging to H, right? And then let us define the event AL as epsilon hat HL uh, minus epsilon HL is less than this mod is greater than gamma, right? So again, what have we done here? Since this result here, right, coming from the Hopking inequality holds for for any given h, right? If I can take any given h in the hypothesis space and this result holds, therefore what I'm going to do is I'm going to just enumerate my hypothesis h1 up to hl up to hk, right? K being sort of the set of all hypotheses, right? And then I will define these events al, right, to be the event that the error, training error of hl, the difference between the training error of hl and the generalization error of hl is more than gamma, right? And I will define this al for all l between 1 and k, right? And given this definition of ALs, right, right, where L goes from 1 to k, right, what I can do is apply the union bound now. So I will get probability of A1 union A2 up to AK is less than equal to probability of AL sum over L equal to 1 to K. Now, what is this quantity, right? This is simply saying the union over A1 to AK is simply saying that when will this union event will occur, right? This will occur exactly when that any of the ALs is satisfied, which is that for any of the hypothesis, if the difference between the training and the generalization error is more than gamma, then this union event, right, the union of these events will be said to occur, right? Therefore what we can write this the left hand side as the probability that there exists an h belonging to h uh, such that epsilon hat h hl or let me right, just call it hl uh, minus epsilon hl, this being uh, more than gamma, this probability is less than equal to sum over L equal to 1 to k of uh, you know P of AL, right? P of AL is bounded by this 2 e to the 2 gamma square m, right? So each of PAL is less than equal to this quantity. Therefore, we can just put that PAL, right? Because PAL, remember, is less than each of these 2 e to the minus 2 gamma square m, right? And therefore, this is equal to 2k e minus 2 gamma square m, where k is the size of the hypothesis space, right? And because this is for right, this is simply the probability that if I take right, that probability of any hypothesis existing in the space such that the difference between the training and generalization error is more than gamma is bounded by this quantity, and we can simply drop this L if we want it, right? So we can just say that the probability that there exists an H such that this difference epsilon hat h minus epsilon h uh, is more than gamma is less than equal to 2e minus 2 gamma square m, right? And this result is called uniform convergence bound, right? This is called uniform convergence bound, and I will proceed with this on the next slide, right? So this uniform convergence bound result states that the probability that there exists a hypothesis belonging to our hypothesis space where the size of this hypothesis space is k. Let me just write it. Is this probability that there exists a hypothesis belonging to this hypothesis space such that epsilon hat h minus epsilon h is more than gamma. This probability is bounded by 2k e to the 2 minus gamma square m, right? And this is called the uniform convergence bound because this is sort of uniformly applied across all hypotheses in the hypothesis space, right? And note that this may not be a tight bound, right? I mean, this is a sort of a loose bound, right? Maybe there is a tighter result that one could state possible in restricted settings, but this sort of applies in general, right? And what we have here is a valid or a sound bound, right? On right, which bounds this probability of making an error, meaning the difference between the training and the generalization error is more than gamma. Okay, and then finally, right, let me just take a few minutes more, is that we can also write this sort of as a negation of this, we can negate this quantity inside, so this will be probability that there does not exist, uh, right, probability that there does not exist, not of there exists in H belonging to H, uh, right? Or actually let me write it differently, that probability that there does not exist in H belonging to H such that epsilon hat H minus epsilon H is more than gamma is less than equal to 2, uh, rather, because I have now negated this, right? So I'm saying, the probability of this event is less than equal to this, right, RHS. Therefore the probability of negation of this, which is, there does not exist such an H such that this difference is more than gamma, is greater than equal to 1 minus 2k e to the 2 minus gamma square m, right? Right, the second sort of expression, the event is simply the negation of the one in the first expression. Therefore, if probability of the first expression is less than equal to some quantity, then the probability of second one, which is the negation of the first one, is simply greater than equal to 1 minus the quantity in the RHS of the first expression, right? And this is nothing but that probability that there does not exist a hypothesis such that this particular this difference is more than gamma is equivalent to saying that for all hypotheses in my hypothesis space, it is the case that epsilon hat h minus epsilon h, this difference is less than equal to gamma. This probability is greater than equal to 1 minus 2k e minus 2 gamma square m, right? So this is another way to state this result, right? And what we will do now is that we will introduce a new quantity delta, which is our confidence. And because right, let me call this number 1, number 2, and number 3, right? And because number 3, sort of the LHS of number 3 holds for uh, you know uh, this 1 minus 2k e to the minus 2 gamma square m, right? So what we can equivalently state is that probability for all H belonging to H, uh, epsilon hat H minus epsilon H, this quantity is less than equal to gamma, uh, is always greater than equal to 1 minus delta, where our delta is right. So now this holds for 1 minus 2k uh, to the e to the minus 2 gamma square m. If I choose my delta to be greater than equal to 2k e to the minus 2 gamma square m, right? If I choose my delta in such a manner, then from uniform convergence bound, right, this this result will hold for all gamma delta, so that such that right, in case such that I choose my delta in this manner, right? And this is following from uniform convergence bound, right? And let me sort of continue here from this in the next class. Thanks.